I guess the only thing that was missed in the recording was the whole fiasco where I couldn't hear anybody. Okay, let's see. How many? Oh, I have 20 out of 23 responses. So when I get all 23, I think I'm going to hit this show responses button and we'll see what happens.
Is there not like an enter button? Well, I'm on my phone.
I've never done this before.
Because I clicked on my answer, but it doesn't. Oh, okay.
Oh, so you just click an answer and that's it? Like it accepts it, done?
No, it doesn't accept it. It just shows like what you clicked on. There's no enter button.
Okay, so you just click on it. Okay. So as long as you click on it, that counts as your response. So I guess technically you could change it. I'm still waiting. I have 22 out of 23 responses. So someone needs to click. Does it tell you? I mean, I guess it doesn't tell you anything. It just has your response highlighted. Okay. All right, we got all 23. So if I say show responses, crazy. Did you guys just guess? Did we just guess? Okay, so when I say show responses, can you guys see this presentation slide? Okay, so you can see what everybody chose. Okay, yep. And it's kind of nice because it's anonymous, so nobody knows if you chose the incorrect response. It's not like when you enter a response in the chat, which I also appreciate because it's really nice that you're giving me some sort of feedback. But then if you give me the wrong response, then you might be like, ooh, now everybody knows who I was and I said the wrong thing. Okay.
Wait, which one is right out of the...
That's a good question. Which one is right? How about we switch my presentation over and I will do this one for you. What's interesting is, oh no, I thought the majority of people didn't even choose the right answer. No, the majority of people did choose the correct answer. It was A, 4 minus the natural log of 8. Okay, so yes, I will do that one for you real quick, and then we'll talk about solving equations unless you have homework questions. All right, well, I'm just really glad that the Pear Deck worked. I'm going to figure out a way to sort of incorporate this, and hopefully, obviously, it would take a lot less time next time just because you've done it before and you're sort of familiar with it. And then I'll look into these other options. Let's see. Oh, yeah. It's so, you know, if you guessed, actually, I feel better about that because if you really worked hard on it and got the wrong answer, then I'd be like, how did they get that answer? All right. Yes. Okay. So let's see. I'm going to stop my presentation and then I'll put my my visualizer up here. Oh, wrong thing. Here it is. Okay. Okay. So your exercise that I asked you to do was the natural log of e to the 4th divided by 8. Maybe I should set up like some exit problems for like, okay, here we're done with the lesson. Now here's something that you can do. So I feel like so I can tell if you learned anything. Okay. So the natural log of e to the 4th divided by 8. Now, when you split this up, we're going to use that quotient property for logarithms, and we're going to turn the quotient into a difference of 2 logs. So we're going to rewrite this as the natural log of e to the 4th minus the natural log of 8. And then we'll simplify. The natural log of e to the 4th is just 4. Remember that the natural log of e is like log base e of e, and the bases match, you keep the exponent. So this was from one of our properties for natural logarithms. And that's it. That was option A. Okay, so that wasn't like the most intuitive thing to put together, but I wonder if it will let me update it in real time. Like if I wanted to add in some questions at the end for you to work on, like if you stayed in this code, if it would update questions in there. I have a feeling it wouldn't, but I'm interested to see. Maybe we'll try it later if we have extra time. Did anyone have questions from the homework?
The homework is due Monday, right?
Yes. Yeah. I mean, it would have been helpful if you could get to the homework beforehand, but doesn't always happen. Yes, we always have homework, Angel. Yes. You had homework from gosh, what if I didn't know I did put up homework? I always am like, oh my gosh, I don't remember putting up homework, but then I remember that I did. Yeah, it was 4.3 and then that last part of 4.2. So graphing logarithmic functions. And then we talked about expanding and condensing, and we talked about the change of base property. Okay. All right. So no questions from the homework? All right, well, thanks for going through that experiment with me. I appreciate all the input that you guys had on Kahoot and everything else, Gimkit and all that. This is not the right thing. This is the right thing. Okay. Also, 8 of you so far filled out my Google form. If you have not seen it yet, it should have been emailed to you. I was kind of surprised to see that not a single person preferred Zoom to Google Meet. So interesting, which is fine. The last thing I need to do is switch to a new platform. I've been in a lot of Zoom meetings, but I've never run one myself. So let's see. Today we are going to be solving equations that involved exponential and logarithmic functions. Now, you're going to see 4 main types of equations today. I have a bunch of different instructions depending on what your equation looks like. We're sort of going to go through these in order. So the first couple of examples you see will follow this form, and then the next set of examples are going to use this form. So you'll really see these go in order, but I'm going to remind you of these instructions as we hit each type. The first type of equation that you're going to see today, and remember these are equations, so you're expecting an answer, like an x equals answer. The first type of equation you're going to see has the form b to the m equals b to the n. And then what you do, as long as you have the same base, is you set the exponents equal to each other. Now, this is not always going to work because sometimes you're not going to be able to get the bases to be the same. But you're going to see in the first couple of examples that we will be able to get the same base on each side. So if you can do that, this is sort of a special thing that you can do in that case. Then we're going to use this property for solving these exponential equations. Now, it's an exponential equation if it's in this form because the variable will be in the exponent. So the thing is, you can't solve an exponential equation without doing a little bit of work to it because you can't solve it while the variable is in the exponent. All right, so I'm going to get to these directions when we get to those examples. But for now, I wanted to really talk about what happens for that first type of equation. Let's see. Losing my focus a little bit there. So the first one is 5 to the x equals 25. Now, these equations don't have the same base. However, they're close because you can write it so that the base on the right-hand side, 25, is the same as the base on the left. So if you see that you can rewrite the bases to be the same, then that's what you're going to do here. Sometimes you'll just have to rewrite one of them, and sometimes you'll have to rewrite both. In this case, we can write 25 such that it has a base of 5. And we would do that by just rewriting 25 as 5 squared. And I find that this is usually pretty intuitive for students. Once you have the same base, it must be the case that your exponents are the same in order for these two expressions to be equal to each other. So 5 to some power equals 5 squared. Well, it must be the case then that that power is equal to 2. That's about the simplest of this type of example that you're going to see, but that's how we do these. That's how we solve these exponential equations, where we're equating the exponents and equating the bases. Now, we're going to do the same thing with number 2. This one's a little bit harder to work with just because you have a fraction over here on the right-hand side. However, you should be thinking about the fact that 3 and 27 are related. So even though 27 is in the denominator, that's okay. You're still going to be able to write 1 over 27 such that it has a base of 3. Now, you know that 3 cubed is 27. And if I want to move that 27 into the denominator, then I need to make the exponent negative. So we can write the left-hand side the same. You don't have to have the parentheses as long as you make sure that you really are careful to show that exponent being in the exponent. You don't want to lose something in the base. And then we'll rewrite 27 or 1/27. If you want, I'll do this in 2 steps just to make sure it's very clear. So 27 is 3 to the 3rd power. So we can start by just writing the denominator as 3 cubed. And then if you want to move that expression to the numerator, just make change the sign of the exponent, which in this case would be making the exponent negative. So on the left, you have 3 to the 6 minus 3x. And on the right, you would have 3 to the negative 3rd power. So with the negative exponents, remember, you just switch its position in the fraction to make it positive. So the goal here was to create an equation such that each side of the equation had the same base. And now we have that. Once you have the same base on both sides, you can go ahead and set the exponents equal to each other. And then you just have to remember how to solve linear equations, which we've been doing for a long time. So subtract 6 from both sides. Don't forget that the left-hand side still contains a negative 3x. And negative 3 minus 6 is negative 9. And then divide both sides by negative 3. Negative 9 divided by negative 3 is positive 3. And if you'd like, feel free to plug that into your equation and just verify that you would get back what you should be getting back in order to make these two equal to each other. So if x was 3, 3 times 3 is 9. 6 minus 9 is negative 3. So 3 to the negative 3rd is equal to 1/27. Does anyone have a question about number 2? All right, so we have one more of these, and this is the kind of example that's not really necessarily difficult. It's just one of those things where you have to be careful with your work, and your parentheses are going to be really important here. 4 to the x plus 2 equals 8 to the x minus 6. Now, you cannot rewrite 8 such that it is 4 to some power. 4 to the 1st is 4. 4 to the 2nd is 16. However, 4 and 8 share a common base. In this case, you're going to have to rewrite both of these bases to be a smaller value. So we're always going to drop the base down. We're not going to increase the value. I can rewrite 4 as 2 squared, and I can rewrite 8 as 2 cubed. Now, be very careful, because when you rewrite 4 as 2 squared, that exponent now has to get distributed into the exponent that you already had. And that's the thing you really need to watch out for here, is just making sure you include those parentheses so that everything gets distributed properly. And do the same thing on the right-hand side. 8 can be rewritten as 2 cubed. Don't forget your parentheses. we're going to take x minus 6 in the parentheses. Now we have the same base on both sides of the equation. We can go ahead and equate the exponents. Now, if you want to distribute before you do anything else, that's fine. If you just want to write what you have and then work on it from there, that's fine too. So as long as the bases are the same, we know that 2 times x plus 2 must be equal to 3 times x minus 6. And then we'll solve that equation. So go ahead and distribute on both sides and solve for x. Get your variable on one side and then get your coefficients all to the other side. And you get x equals 22. Are there any questions about number 3? Okay. I'm so glad that my chat is beeping at me again. Okay, the next type of equation that we're going to solve is going to use this second rule, using logarithms to solve exponential equations. So the equations that we're going to be looking at next are still exponential equations, meaning you have a constant base and a variable exponent. However, in the next several cases, you're not going to be able to create a common base for your expressions, or any sort of integer base anyway. For instance, looking at number 4, solve the exponential equation. We're going to express the solution set in terms of natural logarithms. We have 8 to the 5x equals 4.4. So this is a situation where we cannot write 8 and 4.4 with a common base. When that happens, we're going to follow these rules for solving logs solving exponential equations using logarithms. So we're going to isolate the exponential expression. Now, in some cases, that will already be done, so you can skip that step if that's the case. We're going to take the common log on both sides of the equation for base 10, take the natural log on both sides for bases other than 10. Now, that's a rule that your author uses. Technically, you can use any log you want, but it's most commonly done that you use the natural log as long as your base is something other than 10. So you'll simplify using one of the following properties. B to the x equals x natural log b, or natural log e to the x equals x, or log base 10 of 10 to the x equals x. This is going to be the one that you see most often. If you're not sure where this came from, you're going to see it in just a minute when we apply a logarithm on both sides here. And then we'll solve for the variable. So sometimes we're not going to be able to get these answers down to really nice integers or even really nice fractions. We're just going to have to leave them exact. If I want a decimal, I'll ask you for one. Otherwise, please don't give me any decimal answers. Let's see exact answers. Okay, so the first one is 8 to the 5x equals 4.4. So you're looking at this, it's an exponential equation because there's a variable in the exponent. There's no way that you're going to be able to get these two bases to be the same. So at that point, you're going to choose to take the natural log on both sides of the equation. I'm having some focus issues here today. Okay. So I'm going to take the natural log of 8 to the 5x and set that equal to the natural log of 4.4. Whatever we do on the left-hand side, we must also do on the right because we are looking at an equation. So we can apply a natural log on both sides. Technically, you could also do a log base 10. Now, if you're wondering, okay, what the heck, why did we do that? Well, it's because we can now use that power rule for logarithms that you learned in 4.3. So you had a rule in 4.3. I don't remember exactly what the power was. I think it was log base b of m to the p equals p log base b of m. That's the rule that we're going to be using as we use this particular property. The whole goal here is that we can't solve for x as long as x is in the exponent. So we need to get x out of the exponent, and that's why we applied a log. As long as I apply a log, then we can go ahead and move that 5x in front of the log. Why does 8 equal ln? It doesn't. Oh, wait, never mind. Okay. All right, Angel, you figured it out, your question? Okay. So we applied a natural log on both sides. By doing that, we were then able to use this property of logarithms that tells us that we can pull the exponent out and move it in front. Still don't think I know what ln is. The natural log. Were you in class on Monday, Angel? Okay, so remember on Monday we talked about common logs and natural logs. So ln just means the natural log. Okay, so remember the natural log is log base e. Now we use that property for logarithms. We pulled the exponent out as a constant multiple. Now we're going to solve for x. You have 1, 2, 3 factors here on the left-hand side. If you want to solve for x, everything's already being multiplied. Undo that multiplication using division. I'm going to write this one more time so that it looks really clear where everything is coming from when I divide this out. I just want x on the left-hand side. So I'm going to divide out 5 natural log 8. And when I do that, I just have x equals the natural log of 4.4 divided by 5 times the natural log of 8. And that is the exact answer. When you are asked for an exact answer, that's what it looks like. Don't give a decimal approximation. It's going to be a lot of decimal places. Just leave it as is. Are there questions on number 4? Okay. We'll do another one. However, the next one uses, or it has a base of e, so this one's going to look a little bit different. The base for number 4 was 8. So the natural log of 8, well, we don't really have a property for that. For number 5, the base is e. We need to get the x out of the exponent. The only way we can do that is by applying a natural log on both sides. And now you can use this property for logarithms. Well, you could do 2 different things here. Let me remind you of the 2 things that you could do. When your base is e, you have other options. The natural log of e to the x is just equal to x. So if your base is e, you can just take that exponent out. You don't have to do anything else. If you want to write it as 3x times the natural log of e, fine. But then you're just going to have to simplify the natural log of e as 1. So if you would like to see it that way because maybe you feel more comfortable with that, that's fine. We'll do it that way. And then the natural log of e is 1. So now you have 3x equals the natural log of 8. And then divide both sides by 3, and you get x equals the natural log of 8 divided by 3. Are there any questions on number 5? Okay. I just remembered that we forgot to discuss something at the beginning of class about your test. So technically you have a test scheduled for Monday because chapter 4 is really short. I'm definitely not doing 4 or 5 today because I tend to find that students don't do well with these equations. So I want you to really spend some time with them. The last thing I want to do is cover 4-4 and 4-5 tonight, and then all of a sudden you have this test. My goal is to cover 4-4 with you tonight. And then on Monday, we'll talk about 4-5, and then maybe go over some review from 4-4 and maybe the rest of chapter 4 even, just because it does go by so quickly. And then I think we'll probably just do your test on Wednesday. But I mean, we can discuss. The problem is if we don't do your test Wednesday, then you're going to have to start chapter 5 Wednesday. And a lot of times students don't like to start a new chapter and then like 5 days later take a test on the previous chapter. So we can discuss that on Monday, but I'm going to plan on just having your chapter 4 test next week on Wednesday. Which chapter explains what log? You haven't learned logs. We talked about logs just in chapter 4, Angel. We've been talking about them in 4.2, 4.3, and 4.4. Okay. All right, questions about this or about your exam? Okay, maybe I'll send an email just to clarify, because I know when it's an online class, I feel like there needs to be more communication email-wise, where maybe I wouldn't normally email you all the time. I feel like I need to communicate more, just so everything's clear and in writing. Okay, now same idea here. We're going to solve the exponential equation, but this time we're going to use a calculator to obtain a decimal approximation. Okay, I'm glad you find emails to be helpful, Beth, because I'm concerned that my emails aren't being read by a lot of people, especially after the first test when people were like, it's only letting me upload 1 file, and like, how am I supposed to scan this? Didn't I send like 2 emails about this? Posting to D2L? Yeah, I could do that. Posting to the news? Okay. Simon reads my emails. Thank you, Simon, because it takes me a long time to write them. You know, I want to know that people are reading them. I know they can be kind of long, but usually it's important information. Usually. Okay. Thanks, Karen. You guys are so nice. Okay. All right. So this one is e to the x equals 4.3. Now this is very basic. All you have here is e to the x. There's no 3x. It's just e to the x. You have nothing else on that e to the x. In order to solve this equation, you're just going to apply a natural log on both sides. And then on the left-hand side, you're going to use that property of logarithms to pull the x out of the exponent. So again, I'll remind you, we talked about this on the previous page. Natural log of e to the x equals x. So on the left-hand side, we already have x. On the right-hand side, we have the natural log of 4.3. Now, I believe on your homework, it's gonna, when it asks you for an approximate, I think it first asks you for an exact answer. I'm not positive, I can't remember for sure, but I think it wants both when it asks you to approximate. Now, we talked last week about how to enter natural logarithms into your calculator. But x is just the natural log of 4.3. So you're going to hit, let's see, second. And then oh no, we're entering natural log. Sorry, not e to the natural log is right here, ln 4.3. Then you get 1.4586. I'm using these little squiggly equals because it's not exact, it's an approximation. So just follow the my MATLAB instructions for how far to round this off. Oh, you know, my instructions said 2 decimal places. See, now I'm the one not reading the instructions. That means 1.46. I think my MATLAB is 4. That's probably why I did 4. Oh, who cares? All right, now number 7, same idea. Look at your bases first. If you can equate the bases, you're making your life a little bit easier. But you cannot rewrite 4 and 6 such that they have the same base. I can't use 2. I know you're thinking 2 because 4 and 6 are both even. Well, 2 squared is 4, but 2 to certainly not an integer power will get you to 6. So that's not going to work. So go ahead and apply the natural log on both sides. And then go ahead and pull your exponent out front. Now, be very careful here because your exponent is 2 terms, not 1, 2 terms. So when you pull the exponent out front, you must use parentheses because that entire exponent on the left-hand side has to apply to the base, natural log 4. If you don't include parentheses, then it'll just be x plus 6 natural log 4. That's not what you want. Okay, now remember we have to solve for x. In order to solve for x, you're going to have to distribute because we need to get these terms split up so that you have one term that has x in it and one term that doesn't. So we have x natural log 4 plus 6 natural log 4 equals the natural log of 6. And by the way, this is a much more common type of problem that you're going to see with solving using logarithms. Okay, we're trying to solve for x. You want to keep the term that has x in it on one side, and any terms that don't have x in them, bring them to the other side. So we're going to take off 6 natural log 4 from both sides. And what that's going to leave us with, and we're not going to be able to simplify the right-hand side, but it's going to leave us with x natural log 4 equals the natural log of 6 minus 6 times the natural log of 4. And I'm going to move up here so that I have room to finish this out. Are there any questions at this point? Now, in order to solve for x, you're going to divide out anything that isn't x from the left-hand side and the right-hand side. So this factor of natural log 4 is going to cancel on the left. And your answer is x equals the natural log of 6 minus 6 times the natural log of 4. That whole quantity divided by the natural log of 4. Whatever you do, don't cancel out the ln4s on the right-hand side. You cannot cancel between terms. You can only cancel out factors. And you don't have a factor of ln4 in the first term. Therefore, you cannot cancel out these ln4s. It's a very common mistake. Don't do it. So this is your exact answer. It does not get any simpler than that. Simplified, does not get any more simplified. I don't want to imply that it's simple. Just want to insist that you cannot simplify this further. Oh, another thing you can't do, you can't just go through and cancel the natural log out of every term. It doesn't work that way. It's not a common factor. It's natural log 6. That's just an entirely different number. It's not like 6 is being multiplied by something. So you can't cancel those out. When you put this in your calculator, I want you to put parentheses around the numerator. So we're going to enter the numerator with parentheses. That is an extremely common error that people have here. They get all the way to the end, and then they put this in their calculator, and they forget the parentheses. So what the calculator does is it takes the natural log of 6 and then subtracts off the quotient of 6 ln 4 and ln 4. That's not what you mean. You want to divide this entire numerator by ln 4, not just 6 ln 4. So we are going to put this in our calculators to get an approximate decimal solution. Open up your parenthesis on the left. ln 6. Don't forget to close off your parenthesis for your natural log. Be very careful about how you enter this. Minus 6 ln 4. Now, close your parentheses off for the ln and then close it off again, because now you have two sets of parentheses. You can always count them if you want. The number of left parentheses should match the number of right parentheses. So you have 1, 2, 3 left parentheses and 1, 2, 3 right parentheses. That's what you should have. So this one, the first one, closes off the ln 4. The second one closes off the difference of those two terms. Then divide it by ln 4. You should get approximately negative 4.71. Any questions on number 7?
Yep.
Okay. Okay. All right, those are the methods that we're going to use to solve exponential equations. Now we're going to talk about how to solve log equations. Now you're going to be working with two different types of log equations. One type of log equation is going to have some terms that have logarithms and some terms that have constants. For something like that, I'm going to go back to your initial directions here. You're going to be looking at this third set of directions, using the definition of a logarithm to solve logarithmic equations. So this would be for the case where you have a mix of logarithmic and constant terms. So some of them are going to have logs on them. Some of them are not going to have logs on them. So our goal here is to express the equation in the form log base b of m equals c. Now, sometimes they're already going to be in that form. Sometimes they're not going to be in that form. You might have a constant multiple on your logarithm. You might even have 2 logarithmic terms, or maybe even 3, and then 1 constant term. As long as you have any constant terms at all, this is the way you're going to have to do this problem. So we're going to use the definition of a log to rewrite the equation in exponential form. So we did a lot of going back and forth in 4.2 for writing our logarithmic expressions in exponential form and vice versa. And this is why. We're going to be converting back and forth between logarithmic and exponential form. So we're going to take our log equation and turn it into an exponential equation. Then we're going to solve for the variable, and then we'll check the solution and make sure that our solution only includes values that are in the domain for the log. Remember, we talked about how to find the domain of a logarithm, and I believe that was in 4.2. This value for m must be positive. Remember, we discussed that the domain of a logarithmic function was such that m had to be greater than 0. Oh, also says this right here. That's going to be important. Every once in a while, you're going to solve for your value for m, and you're going to find that it's negative or maybe even 0. And in that case, you can't include those solutions. All right, so I will show you how to use this. Solve the log equation. Be sure to reject any value that's not in the domain of the original logarithmic expression. Give the exact answer. So number 8 is log base 2 of x equals 5. So we went back and forth how to write logs in terms of exponential expressions and vice versa. Remember that you're taking the base to the exponent. So 2, a logarithm is an exponent. 2 to the 5th equals x. As long as you remember how to do that, the rest of your work is going to seem really straightforward at that point. So it must be the case that x equals 32. And then you're going to go back to your original log and verify that if you plug in 32 for x, you're not violating the domain. And you have no issues here because 32 is positive. It is in the domain. Therefore, it is a solution. Any questions on number 8? Okay. Number 9. Are there any Beatles fans? I can't say number 9 without going number 9. Number 9. Yes. So I think they parodied that on The Simpsons because my husband thought originally when I first met him that when I was saying that, I was like quoting a Simpsons episode. I was like, no, 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 no. Number 9. Oh, it's from the White Album. What was it? Not Revolution, number 9. Number 9, number 9. Anyway. They talk about it on The Simpsons, and my husband did. He doesn't catch the Beatles references. Yes, they did, right? I know he was like, wow, you really know your Simpsons references. I'm like, He said he never knew that so many Simpsons references had to do with the Beatles until he met me and was like, I never knew that. Okay. All right. Number 9, notice that you have 2 log terms and 1 constant term. Anytime you mix the logs, yeah, I think it is. It's not my favorite. Anytime you mix the logs in with the constants, you need to combine the logs into 1 log and move all the constants together. So your goal here is to get the logs condensed on one side, and then the constants on the other. Oh, sorry. So remember Monday I was saying that when we're condensing these logarithms, it's not for nothing. You're going to need to learn how to expand and condense so that you can solve logarithmic equations. That is very much the case here. What our goal is we want to turn this, number 9, into something that looks like, I keep putting these away and I should keep them out. Something that looks like this, log base b of m equals c. That's what we're trying to turn this into. So we want to have one log on one side and one constant on the other side. Now, if you remember your work with condensing logarithms for last time, then this will be a piece of cake. If you want to combine these into one logarithm, it's a sum of 2 logs. So you're going to have 2 different things happening. Sometimes it'll be a sum, sometimes it'll be a difference. Remember that if it's a difference, you combine it as the log of a quotient. Because it's a sum, we're going to combine these 2 as the log of the product. Now, I'm using a bracket here just because I feel like it makes things look clearer. I wouldn't say you have to use brackets here. I just think it looks better. Makes more sense to me. All right, so now we have one log on one side of the equation, and then we have one constant on the other. Now, it's up to you if you want to FOIL inside this log now, or if you just want to rewrite this now into exponential form. If I were you, I'd probably just rewrite this in exponential form. You're going to have to FOIL it out anyway. Before I do that, does anybody have a question here? Okay. All right, so we condensed this into one log. I feel like this is the hard part. Even though we did a whole lesson on it, for some reason, pulling that into this, sometimes people don't know when to use it and when not to. So hopefully you're writing some good notes so that you'll be able to use them. All right, so we're going to rewrite this in exponential form. We're going to take the base, which is 4, to the exponent, which is 2. A logarithm is an exponent. And then on the right-hand side, we have x plus 5 times x minus 1. Now, this is a quadratic equation. You're going to have to turn it into a form that you can use. Whatever you do, you can't use the zero factor property here. Sometimes students forget that the right-hand side or one side of the equation has to be 0. You can't say 5 plus x equals 16 and x minus 1 equals 16. You can't do that. Well, we're going to simplify this. So we have 16 on the left-hand side is equal to, we'll have x squared, and then we have minus x plus 5x, which is plus 4x, and then minus 5. Now, to solve our quadratic equation, we will get 0 on the other side of the equation. So let's go ahead and subtract 16 from both sides. You get 0 is x squared plus 4x minus 21. I'm going to move up here. And hopefully we're already thinking about the values that multiply to negative 21 and add to 4. So when we think 21, a lot of times we think 7 and 3. We need these to add up to positive 4. So we'll use negative 3, positive 7. Now we'll use the zero factor property because we have 0 on the right-hand side. Whatever you do, don't put a box around those yet because you're not done. Remember that you need to go all the way back to the original equation and verify that the answers that you got don't violate the domain. Now, don't throw out x equals negative 7 automatically. Don't say, well, negative 7 is not positive, therefore we must get rid of it. That's not always the case. You can have an answer that's negative as long as it doesn't make your log expression negative. In this case, though, if you were to actually use the value of x equals -7 in your equation, you would have -7 plus 5 inside your log. Now, that would be a problem because you would be taking the log base 4 of -2. Now, it doesn't even matter what happens in the second term because you've already shown that in the first term, you end up taking the log of a negative number, which you can't do. As long as you violate that in either term, that's bad news. But you can show it in both. I don't want you to be confused. Oh, I was just simplifying in that step. Okay. -8. So in both cases here, you're taking the log of a negative number. So not good, doesn't check. Get rid of that solution. You can do the same thing for 3. Now, you don't have to show me your checking work. A lot of times you're just going to eyeball this. Like, I mean, you could visually take -7 minus 1 and you know it's 8, and then you could be like, okay, clearly this is not a solution. But on the test, I want to make sure that you found the solution to begin with. Whether or not you show me this work of checking it, not a big deal. That you can eyeball. But what I don't want is for you to go from here to, like, I don't know, here without showing me anything. You have to show me something. Or sometimes people will go from here to here, and I know there's something fishy going on. You have to include your intermediate steps so I can see what you're doing. I would say that all of these steps would be necessary up until you get to here. And then from there, you can say x equals 3. But I mean, I want to see that x equals -7, that you found it, but that you realized, like, nope, this is no good. We can't use that. 3 plus 5 is positive. 3 minus 1 is 2, which is also positive. So x equals 3 is indeed a solution that works for us. And you could always check these also by just entering these values into your calculator and verifying that if you took log base 4 of 8 plus log base 4 of 2, that the quantity would be equal to 2. So you could always do that. Are there any questions on 9? Okay. Wonderful. All right, so number 9 had 2 log terms and 1 constant term. Number 10, I would argue, is easier because it has 1 log term but 2 constant terms. We still have the same goal. Our goal is still to get this in the form log base b of m equals c. So that's what we're going to work on. That means what we want to do is isolate the logarithm and get all of the constants together on the other side. In order to isolate the logarithm, subtract 7 from both sides of the equation. 15 minus 7 is 8. Okay, now you have 3 natural log x equals 8. You don't want something multiplied by your logarithm. You want just the log equals just a constant. So get rid of this constant multiple. Now you have natural log x equals 8/3. You have a log on one side, a constant on the other side. That's exactly what you're looking for. Questions so far? Okay. So once you're here, we're going to go back to that rule. I don't think I gave you the alternative rule for a natural log. Oh, here it is. No, but that's okay. We don't need it. If you want to rewrite your natural log as log base e, if you find that to be clearer, that's fine. I think it will help you in this case. Because I sometimes think you look at this and you're like, I don't know what to do next. But if you see the base there, then you think, oh, no big deal. Take e to the 8/3 and set it equal to x, which is exactly what we're going to do. So you're going to take your base, which is e, to the exponent. A logarithm is an exponent, and set it equal to your argument. And that's it. I feel like that's the most intuitive way to do it. Sometimes though, when you start working with these a lot, students just get used to thinking about e to the natural log of x equals x. If you want to think about it that way, then you could also from here make e the base on both sides. This is probably what you'll do more when you're in calc. Your teacher's probably not going to rewrite this to have a base of e. And if you do that, you're just saying e to the natural log x equals e to the 8/3. And then e to the natural log x is x. So you'd still have e to the 8/3, just getting there a little bit slightly of a different way. Up to you. Whatever you think is most natural for you. Questions on number 10? Okay. All right, number 11. We have, again, a mix of log terms and constant terms. So this is much more similar to number 9. So you have a log term, a constant term, and a log term. Now, just so that you're kind of previewing what we're going to be doing after this, notice that number 12 is a log term, a log term, and a log term. We're going to approach number 12 differently. But because number 11 has a constant in it, we're going to get this in the form log base b of m equals c. So we're going to combine the log terms and we're going to combine the constant terms. Now, in order to combine these log terms, because in the last case that we did this, where we did this, you had the sum of two log expressions. And we took the sum of the two log expressions and we did the log of the product. Come on, there we go. This is going to be different because we have the log expressions on different sides of the equal sign. But no big deal. Let's leave the 3 where it is because we want the constant on its own side anyway. And we're going to subtract log base 4 of x plus 2 from both sides. Now, whatever you do, you cannot combine these. Like, for instance, you can't just say, oh, this must be log base 4 of, like, I don't know what you would do. You would subtract. Maybe you would say x minus x and 5 minus 2. Don't do that. You cannot combine these. You can only rewrite them using subtraction. So you have log base 4 of x plus 5 minus log base 4 of x plus 2. And on the right-hand side, you have 3. Okay, now you're noticing that you still have 2 log terms. Your one constant term is good. In order to combine these into one log term, you're going to use division. So we're going to take the difference of 2 logs and write them as the log of a quotient. So this will be log base 4 of x plus 5 divided by x plus 2. And on the right-hand side, we have 3. So our goal was to get this in the form log base b of m equals c. We have that. We have log base 4 of x plus 5 over x plus 2 equals 3. Once we have this, we're going to rewrite it as b to the c equals m. So let's do that now. We're going to take our base, which is 4, to the exponent, which is 3, and set that equal to x plus 5 divided by x plus 2. And for some of you, it maybe has been a while since you've solved an equation like this. So an example of something I wouldn't expect you to include would maybe be showing this as 4 cubed. I mean, it would be very easy for you to say, okay, 4 cubed is 64, and write 64 equals x plus 5 over x plus 2. But if you went from here to this next step, I might think, like, why didn't they show a little bit more work? So let's go ahead and rewrite this as 64 equals x plus 5 over x plus 2. And then to solve this equation, you can multiply on both sides by x plus 2. We don't want to have that variable in the denominator, so we're going to get rid of it. And you learned to do this when you were solving rational equations back in your 098 class, or maybe in your previous algebra class. You don't want any variables in the denominator. You want to get them all out of the denominator. Also, I want to remind you to include these parentheses around the x plus 2. Otherwise, that 64 is not going to be getting multiplied by both terms. So let's go ahead and simplify. We'll distribute and solve. This is not a quadratic equation, so you don't have to worry about getting 0 on one side of the equation. This is linear. Since it's linear, we just want to make sure that we get all the x's on one side and all the constants on the other and solve for x. Negative 123 over 63. I don't think that simplifies. Oh, it does. If you don't remember how to use your calculator to simplify fractions, hit the math button, enter, enter, and you get negative 41 over 21. Don't put a box around it yet. You need to verify that this is actually in the domain of your original equation. And remember, don't write it off just because it's negative. Before we check this, does anybody have a question about how we obtained the value negative 41 over 21? Okay, so we're gonna, if you would like to just keep this value that's stored in your calculator, I mean, you can kind of eyeball it, you know, it's around -2. If you were to do that and you said, okay, around -2 plus 5 has to be positive. If you weren't sure about this one, definitely plug it in. So you're taking your answer and adding 2 to it. And you do indeed get a positive value. So when x is negative 41 over 21, your logarithm here is of a positive value. So you don't have to worry about violating the domain there. And then clearly negative 41 over 21 plus 5 will also be positive. So in both cases, we still have, I'm going to even write that down, we still have a positive value in the domain. Check to verify. The domain includes this value, which is what we just did. So you're good. And if you want a note on that, we took negative 41 over 21 plus 5, and it was positive, and we took negative 41 over 21 plus 2, and it was also positive. Okay, questions on number 11? Oh, so good question, Beth. What if the answer had violated the domain? Then what would we have done? So let's say you only had one solution and like, you know, maybe like this one was okay, but that one wasn't. If you only had one solution and it violates the domain, then you would be in a situation where you have no solution. So there should be some like hybrid multiple choices on your homework on my math lab, and they'll give you an option to say X equals, and then, you know, separate your answer using commas if there's more than one. And then the other option will be there is no solution. So if that was the case, you would check the box for there is no solution. I'm glad you asked because that does occasionally occur. Anyone else questions on number 11? Okay. All right, so the big difference between 9, 10, and 11 and number 12 is that number 12 has only log terms in it. Now, when we have only log terms, we have a different solution process, and that is the last solution process that you see on the first page. Using the one-to-one property of logarithms to solve logarithmic equations. What we're going to do is express the equation in the form log base b of m equals log base b of n. This form involves a singular logarithm whose coefficient is 1, or a single logarithm whose coefficient is 1 on each side of the equation. So instead of getting logarithm equals constant, we're going to get logarithm equals logarithm. And then what we're going to do is we're going to basically use the same type of idea that we did back here when we had exponential equations and they had the same base. As long as they had the same base, we said it must be the case that the exponents are equal. Well, down here, if we have two logarithms and they're set equal to each other and they have the same base, then it must be the case that the log arguments are the same. So that's what our goal is here. We're going to get log base b of m equals log base b of n. So we want one log on each side, and then we're just going to go ahead and equate what's behind them. We'll solve for the variable, and anytime we have a log equation, we have to check the solution to make sure that it doesn't make your log argument non-positive. So we will do that for number 12. So number 12 is the log of 3 plus x minus the log of x minus 5 equals the log of 3. Now, it's up to you how you want to combine these. Since I'm just looking at these two logs on the left-hand side, I don't really see a point to moving this log to the right. I mean, technically, yeah, you'd have multiplication instead of division, but I mean, you're going to end up doing the same solution process regardless. So I'm seeing a log minus a log. I'm going to turn that into the log of a quotient. Now, it has to be the case, and you're not going to see any that don't do this. The bases have to be the same in order for this to work. Remember, we talked last time about how you can only condense these logs as long as their bases are the same. So I don't think you would see anything where that wasn't the case. I just want to remind you that that's important. All right, so we're going to rewrite this as log of 3 plus x divided by x minus 5 equals the log of 3. So the big difference between 11 and 12 being that for something like 11, we were going to convert to exponential form because we had a constant on one side. For number 12, we're just going to equate these log arguments. So as long as we have a log on both sides, we can just say that what's behind that log has to be the same. I feel like that looks like a 6. It's definitely a 5. So we have 3 plus x divided by x minus 5 is equal to 3. Does anybody have a question there? Okay. Now solving this equation is going to be very similar to what we did in the last example. Multiply both sides by x minus 5. We don't want our variable in the denominator. Can't solve that way. And you now have 3 plus x equals 3x minus 15. And we have another linear equation. So you can go ahead and get all the variables on one side and all the non-variables on the other. And you can do this in one step or two, depending on your comfort level with solving equations. And I got x equals 9. And remember, you cannot put a box around it until you've checked it. So go back to your original log equation and verify. Let me check this. 3 plus 9 is positive. And let's see, 9 minus 5 is positive. Both of those check out. Log 3 doesn't have a variable in it. There's nothing to check there. So 9 is a solution, or the solution to this log equation. Any questions on number 12? It always seems to me that each type of equation on its own is pretty intuitive, but when you mix them all together, that's where the confusion starts. So students will just be like, how do I know when to use this? And how do I know when to use that? You're going to have 2 types of exponential equations and 2 types of log equations. So let me summarize. I do have another, I do have another example, not just like that, but let's summarize. So you're going to see 2 types of exponential equations. One of them is going to be the type where you can equate their bases. So you can rewrite one base in terms of another, or maybe rewrite both bases. So you're going to see that. The other type of exponential equation you're going to see is something like what we did for number 7. So you're looking at the base on each side and you're thinking that there's no way that you can write these such that the base is the same. I can't write 4 and 6 with the same base. When that's the case, you take a natural log on both sides and you pull the exponent out front using that power rule for logarithms. So those are the 2 types of exponential equations you're going to see. Then you're going to see 2 types of log equations. One of them is going to have logs mixed in with constants, something like number 11. So we had a certain number of log terms, a certain number of constant terms. And in that case, our goal is to just rewrite this, or write it so that we have log base b of m equals c, rewrite it in exponential form. The other type of log equation you're going to see has only log terms in it. And you're still most of the time going to be using your skills of condensing these logarithmic expressions, but the solution process changes from there. If you have only logs, you're going to equate the arguments of the logs. All right, so those are the 4 things that you're going to see as you work your way through these equations. Any questions on number 12? Or anything that we've done so far? Okay. So I'm going to try to give you some homework problems that are mixed. I don't want to have you do only one type and then only the next type. You need to get used to kind of working in between them and knowing what to do in each case. Okay, now, when I first gave you this formula back in 4.1 about investments, I always ask you for the accumulated value. And number 13, now that you know how to solve exponential equations, you're going to be asked to find a piece of this equation, usually a piece that's in the exponent. In this case, we're being asked, find how long it takes. When you're asked, find how long it takes, that means find the amount of time t. How long it takes is time. Find how long it takes a $2,800 investment to double if it's invested at 9% compounded quarterly. And we'll round to the nearest 10th of a year. So we're going to use these skills that you learned in 4.1. This time we're going to be solving for a value that's in the exponent. All right, so we're going to find out how long it takes your initial investment to double. Your initial investment was $2,800. That's your principal. It's invested at 9%. Remember, we write that as a decimal, 0.09. And it's compounded quarterly. Remember that n is the number of compounds per year. So compounding quarterly means n equals 4. It's going to compound every quarter. That means it'll compound 4 times per year. Round to the nearest 10th of a year. So let's go ahead and start filling this in. Now, the first thing you see in your formula is A. If you're not sure what A is, we'll come back to it. P we have as 2,800. Then we have 1 plus R over N to the N T. Now you're being asked how long it takes your investment to double. That means that you want to take your original principal, which is 2,800, and you want to have twice that amount. If you're not sure what that is, might as well do the whole thing. Take your 2,800 and multiply it by 2. That gets you to 5,600. Now, some students get very savvy with these double and triple problems, and they're like, wait a second, if this amount is always going to be twice that amount, why don't I just write this as a 2 and then leave this coefficient as a 1? That's fine. If you feel comfortable doing that, that's fine. So on your test, if you said 2 equals 1 plus 0.09 over 4 to the 4t, fine, that makes sense. I get it. But if you're not sure and you don't feel comfortable with that, then fill out everything. Now, our goal is to solve for t. That means that eventually I want to get this 4t out of the exponent. I have an exponential equation and I cannot equate the bases. This base is not something you're going to be able to equate. That means at some point I'm going to have to work on writing a natural log on both sides of the equation. For now, I need to isolate the exponential expression. That means I need to isolate the base to the power. Do that by using division, getting rid of this common factor of 2,800. And here's what I mean. You're going to do this enough times that you're going to say, wait a second, 5,600 divided by 2,800 is 2. And that is where I say, more power to you. Save yourself time and do that. And then if the investment is triple instead of double, then this would just be a 3 instead of a 2. Okay, now I would not start computing the 1 plus 0.09 over 4 because I'm worried that you're going to take this value and get a decimal approximation and then take the natural log of that and end up with these stacking tolerances, and then your answer will be off by a few decimal points. And I don't want that to happen. So leave this exact for as long as you can. The goal is to get this 4t out of the exponent. The only way you're going to do that is by applying a natural log and using that power property. So we have the natural log of t equals the natural log of 1 plus 0.09 over 4 to the 4t. And again, you're going to get really used to doing that. So if you want to go straight from here to writing the 4t as a factor in front, that's fine. So on the left-hand side, you have the natural log of 2. On the right, now that you have a natural log on there, you can use that power property for logarithms to pull the t in front. And I know that we don't like to keep writing the same thing over and over and over again, but please just keep writing it. Hold on to all your digits. You don't want to lose anything. Now, the really nice thing is at this point, you only have factors on the right-hand side. Get rid of anything you don't want. So my suggestion to you would be get rid of the 4 and the ln 1 plus 0.09 over 4. Do that on both sides. And then you're going to get those quantities to cancel out on the right-hand side, and it will leave you with only t on the right-hand side. Don't lose that t, it's still there. So you have t equals ln 2 divided by 4 times ln 1 plus 0.09 over 4. Now that you're at the end and you have the exact answer, here's where I would plug this into my calculator. Before I do that, does anyone have a question about the solution process so far? Okay. So it's really the same thing we've been doing. It just looks more complicated because there's a little bit more going on inside that expression. So you have the natural log of 2. Don't forget to close that off, divided by. Now, in the denominator, you don't have to have parentheses because you only have factors. 4 natural log 1 plus 0.09 over 4. Yes, I want the natural log of the whole thing. You know what? Actually, I'm worried that it's going to divide by 4 and then multiply by the natural log. So we do want parentheses. Sorry about that. I misled you. But here you're okay because it's going to take 1 plus and then it's going to do its division. 7.8 years. No, 7.9 years. 7.79. 7.79. Oh no, I said 10th of a year. Didn't I just say 7.8? I don't know, guys. 7.8 years. So now that you've seen this done, we'll work on the last one and we'll call it a night. If you do have questions, though, I hope you'll stick around for the office hour. Number 14, and this is sort of a preview for what we're going to be doing on Monday about growth and decay. The size of the bear population at a national park increases at the rate of 4.3% per year. If the size of the current population is 108, find how many bears there should be in 5 years. Use y equals y sub naught e to the 0.043t and round to the nearest whole number. Because we're talking about bears. We don't want to talk about fractions of bears. Okay. So let's see, find how many bears there should be in 5 years. So the current population, whenever you see like a y sub 0 or y sub naught, that's now. And that's 108. The value for y is the population that you're expecting after a certain number of years. So let's see, the current population is 108. And then we have e to the 0.043t, and we're using t equals 5. And really, you're not actually going to be using your skills for solving exponential equations here. You're just sort of preparing for what you're going to see in 4.5 for growth and decay, where we use this formula a lot. So y is what the population will be. Y sub naught is your current population. And we're looking at this after 5 years. So you can go ahead and plug this into your calculator. 108 times e to the 0.043 times 5. And all of that gets multiplied inside your exponent. You get 134 bears. And that's it. So next time in 4.5, you're going to use this formula for growth and decay to set up your own, I guess, to come up with your own parameters and kind of work your way through depending on what the exercise is asking for, whether it's growth or decay, and figuring out what the rate is, things of that nature. So nothing too crazy. The 4 or 5 notes, if you looked at them, are pretty short. So my goal for Monday is to go over 4.5 growth and decay. It'll probably take at most an hour at most. You do have that 10-minute quiz to look forward to. And then after we talk about 4 or 5, I just want to do sort of a review of the chapter, and maybe we'll do that on Pear Deck. I almost forgot what it was called. Maybe we'll do that on Pear Deck. I also have breakout rooms on Google Meet now. It's like a newer feature that was added a few weeks ago. So maybe I'll put you guys in some breakout rooms if you would like. You know, some people hate that. I never liked group work. I was never one of those people. But who knows? Maybe you'll like it. So let's plan for that Monday, and we'll plan for your test on Wednesday. We'll kind of see how Monday's going, but make sure your homework is done. I mean, it's due Monday anyway, but be prepared. Make sure that you have most of this chapter mastered heading into Monday, and then we can work out the kinks. And if you really feel more comfortable having a test on a Monday, that's fine. We can move test 3 to a week from Monday, but then we're going to have to start chapter 5 on Wednesday. Chapter 5 is systems of equations, so it's not really related. Up to you. It wouldn't be on your test, but we would have to start it. Okay, so I'll send out an email just to make sure that that's clear, and then I will see you on Monday. I'm going to put up some homework for you, but if you have questions, stick around for the office hour. I'll be here until 7:55, and have a good weekend. You too, Sebastian.